These lectures are on the internet as soon as I can get them onto YouTube. If you didn't get to class or you're stuck in snow or something that might be useful then, go and have a look. So what we're talking about now is the end of chapter 1, which is a very, what I would describe, gentle introduction to the subject, transitioning from the freshman level stuff, which is high school chemistry in the rest of the world, into what is real chemistry, and thinking about reactions and thinking about systems and why they do what they do. And the foundation here is important, the idea of polarity versus nonpolar. You should be able to identify this in any type of molecule you look at, so you can identify where the chemistry will happen. And typically polarity will be in what we call a functional group, and functional groups are coming up in chapter 2. So it's about to get really busy, so keep up. We talked about dipoles, we talked about electronegativity differences, we talked about learning some numbers. What's the most electronegative element? Fluorine, what's its electronegativity value? 4. What about hydrogen? 2.1. Carbon? 2.5. So most people have got that in their heads now. Good. You will need that for the rest of my class and also biochemistry to go in that direction. Well, these differences in electronegativity will give you dipoles. You'll see now electron shifts in the bonds between atoms that have different electronegativities. So in a molecule like this, where we have this chlorine and this carbon, carbon loses out. And so the electrons in this bond, let's not forget what's happening here. The electrons in that bond are pulled closer to the chlorine because it's more electronegative. That makes sense if you do 2 chlorines. You can see here a dipole in that direction, or a dipole along that bond in that direction. The overall direction of the dipole then is an average of the 2, and the average of the 2 looks like over there. If you're not comfortable with that, you need to get comfortable quickly, because this becomes very important in the lab, and the labs start for real next week. Why isn't there a dipole in this one? They all cancel out. Yes, they're all pulling equally in directions that then cancel out, so there's no actual dipole. This will get confusing when we start doing chemistry of these molecules, because that carbon in the middle, no doubt, is delta positive because it's losing out to chlorines, but because there's a cancelling out overall, there's no dipole. It's actually a non-polar material. Well, we worked our way quickly into this table. We said not to worry too much about the actual details. I'm not going to talk about numbers necessarily. I will talk about high polarity, low polarity, based on this principle. I'm not going to ask you to memorize any of these values. But we'll work out very quickly that things like water and methanol are very, very polar. They dissolve all kinds of polar material. But things like pentane down here, when we get into the alkane section, these are like crude oil. This stuff will not dissolve in water. And the answer is because, or the reason is because they're incompatible. We will have polar material likes polar material, and non-polar material likes non-polar material. And if you mix the two together, they tend to separate. In the lab, that's very important because we can do actual physical separations of material by doing that. When you get to the extraction experiment in a few weeks, you'll actually do this. But you'll find now that organic chemistry is organized in a very sort of efficient but also versatile way. There's a sort of a continuum here. There's a sort of a range of polarities, and we can use that in the lab to great effect because we can choose our solvents appropriately for what we need to do. Now in biology, you're kind of stuck with one solvent. What is it? Water, right? So we've got to learn about organic chemistry to take it into water, which is pretty much, not a very friendly environment for most organic chemicals, but somehow it works. And we have to, over the next year, or maybe for some of you 2 years, work out how that's the case and how that's possible. But it starts here by learning these very basic principles. So to finish this chapter up, we started on Monday talking a little bit about physical properties and this idea of boiling. And again, if you want to extrapolate that down to melting. The idea that molecules are held together amongst themselves by different forces, intermolecular forces. And it's very important you recognize the difference between the two words. Intermolecular, between, and intramolecular, inside the same molecule. This idea is intermolecular, where you have one molecule next to another molecule, and they may or may not be attracted to each other. Those attractions will be obvious things like delta plus, delta minus interactions. There'll be lone pairs going after protons, things like that. Hydrogen bonding that you've probably seen in the past. It's not difficult. You just have to learn it quickly so that we can use it. So I have some facts up on that slide. The molecule on the left, isobutylene, is a typical alkene. We can look at sp2 carbons here. We can look at the fact that there's no delta plus, delta minus. And its melting point is negative 140. Its boiling point is negative 6.9. So what's its physical state at room temperature? It's a gas. It certainly is a gas. Now, you'll get acquainted with acetone quite quickly because acetone is what you'd use to wash your dishes in the organic lab, right? There's a squeeze bottle at the end of the lab bench, and you'll use that to wash off all the stuff you use during the semester. Its boiling point is quite high. It's 56, positive 56 degrees. So what physical condition is that in at room temperature? It's a liquid, but it's considered to be a fairly low boiling liquid. It evaporates quite quickly. And I'll say this again and again as we work our way into the chemistry, but the sort of playing field that we deal with as chemists isn't that broad. it's about negative 100 degrees up to about positive 200 degrees. Getting below negative 100 degrees is difficult in the lab. You really have trouble doing that. And getting above 200 degrees in the opposite direction starts to destroy molecules. It starts to break bonds and break molecules down. So we're going to work in this range of about negative 100 up to plus 200 and a 300 degree range there. So this difference, negative 6.9 to 56.3, is actually a big difference on that scale. It's a big chunk of that scale. And you should be thinking now, well, there isn't a big difference in the molecules themselves. There's only actually one atom really different. The molecular weights are very similar. The structures are very similar. But all of a sudden, we've got a vast difference in their physical property because of the presence of an oxygen, which is absent in the alkene on the left. So it's all down to the dipole. It's all down to the fact that in the molecule on the top right, I can certainly write, what am I going to put on the O? Delta negative or delta positive? Delta negative, okay, and delta positive down here. So you bring a second molecule of this over towards this, you're going to get an attraction between the delta negative end of that and the delta positive end of the other carbon, of the other molecule. And this just goes on and on and on, sort of macroscopically in terms of this expanding between molecules. And that force, that interaction between those molecules is why it takes a higher boiling point to break them apart. So don't forget, boiling is not chemical reaction. Boiling is just physically breaking molecules away from each other, and that is a dramatic difference. And you'll see as we work our way through now, this is going to be important. So there's not too much that. There's a little bit more in terms of things like what we call hydrogen bonding. You should have heard of that before. The attraction of a delta positive proton for a lone pair. So the basic idea here is you must have lone pairs, and you must have a proton which is delta positive. And of course, if you put a proton on an oxygen and make an OH group, inherently that proton is delta plus, yeah? Because the electronegativity of H is 2.1. What's the electronegativity of O? 3.5. There's a big difference. So we definitely have, in a molecule like ethanol, we have a delta negative on the O and we have a delta positive on the H, plus we have the sticky lone pairs. We'll use the lone pairs to stick to other things. We'll see now again dramatic boiling point differences. If I'm on a 300 degree scale, the difference between these two molecules is 100 degrees. That's a third of that scale. That's a big difference. And I can see some of you are practicing the problems in the first chapter. That's great. These both have the same formula, the same molecular formula, but they have different ways they are put together. What are they described as? Constitutional isomers. Yeah, they're constitutional isomers. And it turns out now, you know, we've got this very important idea that this stuff is completely soluble in water. This stuff is insoluble in water. This stuff, you know, if you drink enough of it, it'll kill you, but it's not overly poisonous. If you drink this stuff, you're in trouble. So there's a big difference now in the pharmacological properties of these molecules and the chemical properties of these molecules and the medicinal properties of these molecules based on the simple relocation of one atom in that molecule. That's a big difference for a small change. And the physical difference now, 100 degrees on our scale, is huge. So this can have intermolecular forces, because you can draw delta positive on the carbons, you can draw delta negative on the oxygens, and you will get some interaction, but still not a great deal. If you're boiling at negative 23, you're a gas at room temperature. There's not a lot holding those molecules between each other. But if you go to ethanol, which boils at 78 degrees, you still have delta plus, delta minus, but you also have the possibility of hydrogen bonding, and that is shown at the bottom. You can see now the delta positive H of one piece is attracted to the lone pair of the other piece. That's a hydrogen bond. They're worth about 3 kilocalories per mole, which isn't a great deal. A carbon-carbon bond is worth about 100 kcal, so it's only about 3% of that. But that's significant when it starts to add up. You think about water. What's the boiling point of water? Don't get this wrong. 100 degrees. That's a huge boiling point, high boiling point for such a small molecule. And the answer again is because you get all this sort of three-dimensional complexation between the molecules in hydrogen bonds, and so they're held together quite tightly, and it takes quite a lot of energy to be able to break these things apart. So hydrogen bonding is important in my class. It is very, very important in biochemistry because it drives an awful lot of the biosynthesis that you have to worry about later. So recognize that the requirements for a hydrogen bond are some delta positive hydrogen and some lone pair. You'll see this, how important it becomes. Can I hydrogen bond to this thing over here? Probably not, because it's not delta positive. So there are some places that this will happen and some places where it won't. Is everybody happy? This isn't physics. It could be worse. Okay. Finishing this thing up, again, looking at series, you should be able to recognize patterns. You should be able to put together fairly simple principles to understand what's happening here. 3 molecules that are closely related. You're simply adding extra carbon pieces as you move from left to right. When we get into the alkane chapter later on in chapter 4, we'll start naming these things. Butane you might know is lighter fluid, pentane you might have heard of, hexane you can use for a solvent in the lab. They're not that different, but they're adding extra pieces along that sequence. They're actually not isomers, they're analogs. And we can say now that the boiling point here changes. It goes from 0 to 36 to 69. Not a big difference. And if those kind of numbers, if this is sort of turning you, off and you're not sort of seeing the differences here, science is all about numbers. Biology is all about differences. You've got to recognize differences and interpret them. So one is 0 degrees. It's a gas at room temperature. The next one is a liquid at room temperature. The next one is a fairly high boiling liquid. And all we're changing here is adding extra carbons. Well, there must be something going on here that allows for interaction, even though these molecules are not particularly polar. So we've probably heard this before, dispersion forces, London forces, things like that. The idea that nuclei in one atom or one molecule are going to attract the electrons in other bonds from other molecules. And when you add these things together, it's like a zip, right? A zipper. The more of these interactions you get, the tighter they're held. So if you start putting these alkanes and you make them into 50 carbons, so you've got 50 carbons in the zip and 50 carbons down here, they can become solids. A lot of gases, a lot of liquids, a lot of solids, but because of the interactions and the sort of increasing interactions, as the molecule gets longer and bigger, you can go all the way from gases to solids in that series, even though there don't seem to be any dipoles in that molecule. I think those are things you've seen before, so that's pretty straightforward. There are some issues that we will deal with extensively. We will talk about how organic reactions are tuned, how we can think about what will go in what pathway. This molecule might go over here, this molecule might go over here, based on size, based on the steric environment. This idea of bulky things getting in the way of other things. So this is the first example of that. All we're doing here is going through an isomeric series of 5 carbons. On the left, I have what I describe as the straight chain molecule. It doesn't look like that in reality. It looks more like this. We'll talk about the zigzag patterns when we get into chapter 4. But it's a straight chain. And you'd have to argue that a straight chain can get close to another straight chain. There's nothing really in the way. They're fairly compatible. But if you start putting bulk in the way, if you start putting an extra group sticking out from that chain, it's going to get in the way. Instead of my hands coming together like this, they're coming together like this, and my thumb's going to get in the way. Ow. My thumb's going to get in the way, and that's going to block things off. So this chain cannot get as close to this chain, and they're not going to be held as tightly. So therefore the boiling point changes, and it goes down, because the interaction is not as good as it would be in a straight chain molecule. And you can see it's consistent, because as you go to the sort of globular 3D molecule, where we've moved things around so we made it sort of a sphere, a ball shape, the boiling point went down again, because those chains can't get as close to each other, and there isn't going to be as much interaction between one molecule and the other, and that means a lower boiling point and less heat to be able to break them apart. There's nothing tricky about this. Get it, understand it. If not, come and ask. Last slide. Sorry, penultimate slide. I've mentioned the sort of progress here, the sort of what we have to do in the next 9 months is to get to some place where you can conquer things like biochem, or you can think about polymer chemistry maybe for the engineers. Biochemistry, for anybody who's interested in medicine or clinical laboratory science or any subjects on that end of the scale, this is important. This is difficult, but it's important. The idea that nature has tuned a whole bunch of molecules to do certain jobs. And we'll find now that you can have molecules that have both properties. They can be polar and they can be non-polar. Not necessarily all at the same time in the same place, but if you looked at something like this, which is an example of a soap, we'll deal with this again later, but we have a very polar end. Why is that polar? It is a salt. Things don't get much more polar than salts, right? NaCl. This is still a negative charge, it's a salt. And that will be attracted to water. That stuff will be what we say hydrophilic. It is going to dissolve in water. But then it has this long alkyl chain at the end, which is very non-polar. And we'll call that hydrophobic. It doesn't like water. So we find in nature and in sort of some of the technology we use these days to clean things, for example, that we can use these molecules to do jobs. We can think about where those alkyl chains will like to go. When they aggregate, when they come together, they would like to be with each other. And we will think about where the salt piece would like to be. It would not like to be with the non-polar pieces. So chances are this molecule will not wrap around on itself. It will aggregate with other molecules like itself, right? And the polar ends, in this case, if this is water outside, the solvent in this case is H2O, so there's water out here and water out here, the polar ends present themselves to the water. And then the non-polar ends huddle together and they form what we call a micelle. More detail later, but this is an aggregation. Where have you seen pictures like this before? Anybody who's taken a general biology class should recognize this type of picture. What is it? Where have you seen this before? Where head groups, polar head groups, line themselves up in a row, and all the non-polar tails end up in here. Cell surface, yes? Cell surface aggregation. So that's very basic organic chemistry, which will eventually lead into things like cell biology. Fundamental ideas. So my last slide is this. You're about to start lab. It's a very gentle introduction, talking about the computer setup to learn about some properties of molecules. Then you start the experiments the week after in the lab. But you've got to keep on your toes in lab. All that information you pick up is important here and vice versa. The idea now that we have a whole broad range of organic molecules in nature that do different jobs. So everybody's aware of things like cholesterol. It causes all kinds of problems. If it precipitates from the blood, you've got problems. Why should this precipitate? Is it polar or non-polar overall? All of this is carbon and hydrogen and carbon and hydrogen and carbon and hydrogen. It has one OH. Do you think on the bulk of that molecule, on the sort of looking at it overall, do you think that thing is soluble in water or insoluble? Insoluble. It is insoluble in water. You think about water being the solvent in biology, that can be problematic, yeah? If it's not going to dissolve in water. Now, sucrose, what do you use sucrose? What is sucrose? Table sugar. And you would hope that table sugar dissolves in your coffee, right? So it dissolves in water. Why does it dissolve in water? What's the difference between this molecule down here and the one above it that makes this one dissolve in water? It's very, very polar, and it has the potential for what? Hydrogen bonding. Hydroxyl, 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 completely soluble in water because it's very polar, it has the same type of properties, and it can extensively hydrogen bond with the solvent, so it dissolves up. We will find out very quickly if you're comfortable with these physical ideas, dissolution, evaporation, things like that. There is a lot of sort of naivety in this area that comes out in the lab. We'll talk about it in class, we'll try and get rid of some of that stuff so that you have a real idea of what's happening. If you dissolve sugar in your coffee, does that sugar disappear? Has it gone? No, it's still in there, but it's in solution. How do you get the sugar back? Evaporate the coffee. You let the coffee sit for a while and it disappears, you've got your sugar back. So that's a very simple idea that you have to take with you into the lab. Everybody okay? I'm done with one. Guess where's next? That's right. Homework out there to be done. Quiz problems to be done. Keep up. Now, chapter 2 is dry until you get to the second half of it. Chapter 2 requires an awful lot of attention because these are the basic building blocks of the chemistry we'll do from now on. We'll talk about functional groups, we'll talk about how to draw organic molecules, and this can be a bit frustrating. In freshman chemistry, it's all about details. Remember the significant figures stuff? If you got the significant figures wrong, you got points taken off? Yeah, not doing that here. But we do have a lot of detail to worry about in terms of what's in this product, what's in this molecule that we can look at. So why do we need to do this? Well, when you get into sort of my end of organic chemistry, the medicinal end, where you're interested in pharmaceuticals and training people to work in that industry, you're looking at huge molecules like these. Taxol on the top left is a very important anti-cancer compound. It is isolated from natural sources. It's been made in the lab. It's quite expensive because it's quite rare, but it does its job. And it contains a huge amount of information. That's really what organic molecules are. They're expressing information. You can see now what looks like a 6-membered ring. We'll call it a benzene ring later. We can see a 4-membered ring over here. We'll call that an ether when we get there. By next week, or even by this weekend, if you want to do well in my class, you ought to be able to look at a molecule like Taxol and tell me every single functional group in that molecule. How do you do that? You take your time, do it stepwise. We start to introduce methods that people use to do well here. Flashcards, these little index cards you can get. Functional group, maybe put the name on the back so you can test yourself quickly. Study sheets, people will go home and condense what we did today into a 1-page abbreviation, so you have the basics down there. It takes time, but this class takes time. Morphine, obviously, is an important analgesic. Lots of 3-dimensional characteristics here. This wedge and this wedge means something. This dash means something. Very, very complicated molecule. Down here, brevetoxin B. We make this in the graduate classes. It's 147 synthetic steps from starter materials. Now, in my class, we get to about 11 steps, maybe 15 steps, in terms of making molecule A turn into molecule B, turn into molecule C, turn into molecule D. You might do 15 steps by the end of 3720. This took 147 steps. So people are thinking about making these things because they're interesting medical compounds or medicinal compounds, but also they look nice. Okay? We want to make them because they look cool and they present challenges. But what we need to worry about now is that you really don't know just yet what is going on here or what is going on here, because I don't see any carbons. And that's kind of the point. We don't have enough time to draw all the carbons in, so we remove them. We assume that they are there. So we're going to do something that is sort of counterintuitive from general chemistry. Instead of all the detail, we're going to take the detail out, because that detail is overwhelming. And we need to strip it down to its basic idea, because guess what? These carbons don't do anything. They actually don't do any chemistry, for the most part, at least at this level. It is the functional groups that do the chemistry. So what do I mean by a functional group? I mean oxygen-containing bits and pieces. Why do they do chemistry? They're delta positive, delta negative. They're attracted to other delta positive, delta negative things. They will react with each other. Hydroxyls do lots of chemistry. We keep those in, but we take all the carbons and as many of the hydrogens as we can out. So this becomes a little bit frustrating because we're going backwards now. If you've been practicing some of the homeworks in the first chapter and you've been looking at my stuff, you'll already recognize this idea of constitutional isomers. The idea that you can put together molecules in different ways using the same atoms to get different outcomes. It's just like building Lego bricks in different ways. We have from very early on the Lewis structure, showing some lines to show where bonds are, showing dots to show where lone pairs are. I'm going to say again, lone pairs are absolutely essential here. In this chapter, we say where they are, we'll tell you where they are, and you must put them in all the time. The lone pairs must go in because that's where the chemistry will happen for the most part. Well, that's a lot of sort of extra work for a small molecule. There's not a lot going on in that system. So what we can do is strip it down a bit and call it a condensed structure. So what we've done here is understanding, you don't know this yet, but you will, understanding that that CH3 group doesn't do anything. It does not do any chemistry. So we just reduce it. We can call it a CH3 group. And as we work into chapter 4, this will become apparent when you want to draw a reaction or draw a molecule very quickly. You can't put all that information in, so you strip it down. If you only have a typewriter, you don't have any of these modern programs to draw molecules, you might write the molecule like that. It is showing, and I've not used this word yet, but I need to use it a lot, connectivity. Okay, connectivity, how the atoms are joined together. So these are all different representations, and the first three representations give you an indication of the connectivity of the atoms and groups in that molecule, how they are joined together. The formula on the right does not. The formula on the right is simply a molecular formula. There might be other ways of putting this molecule together to get a different molecule. That doesn't give you a lot of information. In my class, you'll spend a lot of time with this type of thing and a lot of time with this type of thing for small molecules. But as the molecules get bigger, it's impossible. You can't put all that information in there. Structural isomers, constitutional isomers. Now, if you were to take C3H8O, you can put it together in different ways and get different molecules. If you look at this, we have what we call isopropanol, just rubbing alcohol that you can buy at the grocery store. We have propanol itself right here, which is a different isomer. What has changed? The placement of the functional group. On this, it's on carbon 2 of the chain. On this, it's on carbon 1 of the chain. They are not the same molecule. They are both alcohols. You can expect them to have high boiling points because they're going to have hydrogen bonding possibilities, but they are not the same system. And then we can move to this, which is an ether. We're about to introduce what an ether actually is. And you can see now the oxygen has moved into the middle. Now, of all those molecules, which should have the lowest boiling point? The one on the left, the one on the middle, the one on the right? The one on the right. This is where those clickers would come in handy, but I just don't like those clickers. It's the one on the right. Why the one on the right? It has no hydrogen bonding, absolutely. 1-0 Joe. Okay? It has no hydrogen bonding. So that's what we just talked about previously. Now we're applying it very, very quickly. So let's move into complex systems. Let's think about why you have to strip this stuff down to its basics. You can see amoxicillin at the top. Amoxicillin is a fairly common antibiotic. And it is a complex molecule. We have an awful lot of carbons in there. I can count maybe 20 carbons. I can see 3 or 4 nitrogens. I can see 3 or 4 oxygens and a sulfur. If you were to try to draw this, if you try and draw this on an exam, or talking to a chemist as you're trying to solve a problem or come up with a new reaction, it would take forever. And it's unnecessary, because most of the carbons in that molecule will not do anything. They're inert. It's the molecule, or it's the part of the molecule that typically has the delta plus, delta minus, or electron-rich, electron-poor areas that will do chemistry. So what we can do, and what you need to practice as soon as you possibly can, is turning that into that, and molecules like it. And also going in the opposite direction, because this is where people get lost. We'll do some problems in a second asking how many protons are here, how many hydrogens are here, how many carbons are here. And you have to be on your toes. What's the maximum number of bonds a hydrogen can form in this class? 1. What's the maximum number of bonds a carbon can form? 4. Okay, 4. That's it. So we can take this system and we can say, all right, the hydroxyl is important because it's a functional group as it's about to be defined. It is a part of a molecule that's going to react. This thing here is a carboxylic acid. We're going to keep that in because it's an important part of the molecule that will react. They are the functional pieces. But I've got rid of a lot of information here. That's a CH3 group. Over here, that's a CH group. How do I know it's a CH group? Because I can count to 4. I've got, from that carbon, 1 bond, 2 bonds, 3 bonds. How many hydrogens do I need to be happy? 1 to make the octet. Keep practicing this stuff. It's not difficult at all. So we reduce things down quite dramatically, quite quickly, from big, elaborate systems that have all the atoms expressed into what we call bond line structures. And this is now going to be the way we draw the molecules for the most part. We can see here fairly simple systems compared to where we just started, but this is why we have to start here. What's at the end here? What type of group? CH3, CH2, CH. CH3. What is in the middle here? CH2. What about at this end? CH3. What about right here? CH. So what you're doing, hopefully, is realizing I'm looking at 3 bonds. I need to have 4. There's 1 hydrogen left. Because we're taking out the hydrogens because often they don't do anything, and it's prohibitive to be able to draw those things. What's over here? CH. What's at the top of this guy? CH3. Straightforward for the alkanes. Then you've got to go to the unsaturated systems like the alkenes and the alkynes. And then it becomes a bit more tricky. We have taken quite a lot out of this from its basic structure, its Lewis structure. How many hydrogens here? 1. I've got 1 valence here, 2 valences here. I've got 3 valences, so there's 1 missing. That's going to be a CH. What about right here? 1 hydrogen. What is this group at the end? CH3. Practice, get it, because otherwise it's tricky. It's impossible, pretty much. What's this at the end? CH3. Now, alkynes, when we get there at the end of the term, they are becoming more and more important these days, especially in things like cellular engineering, so we have to be happy with these compounds. There's something happening here that confuses people. That junction between that line and that triple bond is the carbon. So what's been done here is the carbon has been stripped out. It's a carbon with a triple bond to another carbon, and then it's bonded to an H. Be careful with that one. People get lost. They do some strange things here. But this now is showing you that type of arrangement. So how many hydrogens on this carbon? 0, because I got my 4 valences already. 3 to the other carbon, 1 to the methyl group, and that's it. You're done. Questions? It's a very simple thing to get wrong. If that makes sense. Don't get it wrong. So we can go again and look at these types of molecules. If you pick that up very quickly and you already know this, we can look at this type of system and we can say, all right, what's this at the end? It's a single line pointing out into space. What's there? CH3. We've got some hydrogens in here to show stereochemistry. How many hydrogens on this carbon? 0. Right, that carbon's got 4 bonds already. You don't need them. How about over here? How many protons or how many hydrogens on that carbon? Just the 1. You've already got 3 bonds there that are shown. The 4th one is a hydrogen. What about down here? How many hydrogens on that carbon and the alkene? Just the 1. Simple as that. Something as complex as Taxol, you can apply the same deal. And this is always on my first test. It's always on my first test. Some big, ugly, scary, intimidating molecule. And your job at that point should be to look at it and say, oh, that's not so bad. I know hybridization patterns, I know shapes, I know functional groups, and I know this type of deal. And apply it. So how many hydrogens on that one down there? 1. What's missing from the oxygen? What should be on the oxygen that I'd like to see? 2 lone pairs. 2 lone pairs. So very quickly I would expect, especially for those who are going to do well here, that this type of system becomes, nice to look at. They are attractive molecules, they're very complex molecules, and you are building up a method to decode them. It's all about decoding what's going on there, and we are starting that now. Nothing too tricky so far. Well, now I'll probably spend the rest of the morning on this and get it out of the way. And then Friday is the resonance lecture. Okay? Resonance is going to be one of those things that makes you scratch your head violently. So I'll probably spend a whole class on that and get chapter 2 finished on Friday and then to 3 next week. Functional groups do stuff. They do chemistry. Things that are not functional groups tend not to, at least at this level. So we need to build up a sort of vocabulary. These are the bits and pieces. These are the words that we have to worry about to be able to do this subject. We can see a bunch of them. I have a table. Right? It takes 2 slides. Can you memorize this? You have to. There is a certain amount of memorization required. It's like learning a new alphabet. or it's like learning, a new language. You have to memorize certain things. I've got a whole bunch of stuff from the first semester. We talk about all of this stuff in the first term, all of this stuff, all of this stuff, all of this stuff. We talk about that, we talk about that, we talk about that, we talk about this in the second semester. So those functional groups are all 3719, the rest of them are all 3720. And we will do every one of them. Why are there 27 chapters in this textbook? Because each of these functional groups demands their own chapter. They're complicated, they do lots of chemistry, and we have to study it in detail. And then again, when we go further on, carboxylic acids, everywhere in biochemistry, amides, they hold your proteins together. We understand the basic chemistry, we can go further and do the biology. Everybody all right? Benedetto, you all right? Keep the noise down. Giovanna's busy. That's a complex molecule. That is no doubt a complex molecule. We've got lots of things going on in that molecule. Those of you who passed my class this first time round, because you're listening, you're taking notes, you're not bothering your neighbor, will like these molecules. Not everybody can do this. This is why they're set in 3720. It's an awful lot more comfortable in this room. Not everybody can do this. If you look at that and you see a challenge, a bit of fun, great. You look at that and think, holy crap, this isn't going to be good. Do something else. So functional groups do chemistry. I have in this molecule what we call an amide. I have a secondary alcohol. I have an ester. I have an ester here. I have a ketone there. Secondary alcohol. I have an ether right there. I have an ester there, and a tertiary alcohol right there. You need to know what each of these things are soon so that we can start to apply them. And 4 weeks, actually 3 weeks away now, my first exam, there'll be something like this. It won't be this molecule. It'll be something equally as ugly and scary, and you will have to interpret these pieces. So we start. Again, on my website, I have a tutorial there for functional groups. You can play with it on your phone. You can, you've got a few spare minutes, look at these things as you're walking around. We're going to see a lot of alkyl halides. This is a functional group that does a lot of things. This is a very, very useful synthetic piece that is going to enable us to make bigger molecules. There are not a lot of alkyl halides in nature, so we typically have to make them. We have carbon pieces, which are nonpolar, and we have a halide attached. So we have a one-valent halogen from the right-hand side of the periodic table, which tends to be electronegative. So we'll see as we get to that chapter, these pieces tend to be delta negative, and the carbon next to it tends to be delta positive. We are a long way from doing this. We'll get through chapter 3, which is the first chemistry you see, but we are a long way from doing carbon chemistry. But we'll find very quickly that over here, there's nothing. All the chemistry happens at this end of the molecule, because that's where the dipole is. Recognize that early on, you might get into this pretty quickly. We can see now fluorine is attached to a different carbon. We'll have to classify those things a little bit later in terms of their categorization, whether they're primary, secondary, or tertiary. Right now, you see a halogen attached to an alkyl group or a carbon-based group. It's an alkyl halide. Iodides, likewise. Bromides, likewise. Very quickly, we're building diverse pieces to be able to put them together. So recognize now, halogen, alkyl group, that's an alkyl halide. Alkenes. This kind of follows the sequence of the chapters of the 2 semesters. It kind of adds things up. We've got alkenes with double bonds which come in this semester fairly early, and they do all kinds of chemistry. This is one of my favorite chapters. In fact, they're all my favorite chapters. Let's just get rid of it. This has got a huge number of reactions, alkene chemistry. We need to make them, we need to understand them, we need to name them, we need to recognize them. So I have double bonds. I have a hybridization change. On the previous slide, everything was sp3. What's the hybridization now at this carbon? sp2, because we have a pi bond. You should be able to draw those patterns from scratch without memorizing them because we've practiced them. We can see as we go through to things like vitamin A, lots of alkenes. How important are these things in biology? Yes, incredibly. Vitamin C over here, alkene present. So those molecules contain a double bond. Carbon-carbon double bond is the basic structure you need to be an alkene from now on. Alkynes. Alkynes always kind of got ignored until they got really interesting. There's at least one Nobel Prize coming up with alkyne chemistry in it in the near future from California. And these compounds show up quite a lot in nature, but they're incredibly useful in the lab. And we will spend a lot of time at the end of the term using alkynes to knit them together, to take smaller pieces to build bigger pieces. A lot of this is molecular engineering, designing the product. You're given a molecule that you have to make, and you have to put it together. And a lot of it in this semester is based on alkyne chemistry. So you can see here, this is a poison from a frog, tetrodotoxin. and it has alkynes. It's a complex molecule with 2 alkynes at the end from nature. What is at the end of this? There's not a line sticking out of it, so what is at the end of it? A hydrogen, 1 hydrogen. And what's the hybridization of this carbon right here? sp. That sp, I think, is the most confusing of all of them, so practice it and be happy with it. So alkynes, there's all sorts of interesting literature out there about alkynes. Chemists can be a bit odd, let's put it that way, scientists in general, I suppose. There's a fellow in Texas who makes these types of molecules. He calls them nanoputations. Right? It's like a kid's education program. He's trying to make kids interested in chemistry, and he's built these compounds to look like people. Why not? Yeah, why not? If it gets people interested in this stuff, why not? And so this is an organic molecule that looks like 2 people dancing. And you can see what's happened here is he's used the alkynes as linear. That's fun and trivial, but this is the important thing, for example, in medicinal chemistry, trying to build drugs. That sp-sp system, what shape is it? It's linear. So your pieces sticking off of that are pointing in opposite directions. If you need that to build a person like this, or you need it to build a drug, you use an alkyne. If you want this piece over here and this piece over here, put an alkyne in the middle. If you put an sp3 carbon in the middle, they go off in different directions. So these fundamental building blocks are going to become important to design a system specifically for what you want. And we will get into quite a bit of that. Alkynes, triple bonds, carbon to carbon. Alcohols. I would say these are possibly the most important, most useful functional group that you will deal with. I just finished teaching 3720 over the summer, and again it came out that alcohols are central to everything. You understand alcohol chemistry, organic chemistry falls into place. Alcohols are really useful because they're everywhere, they're cheap, you can get them on bulk or in bulk, and they're very, very useful for chemistry. I have at the end here delta negative oxygen, delta positive carbon, proton I should say, and a delta positive carbon. That little part of that little molecule will be very important to you. You will be studying this thing like crazy because again it's central to what we need to do to go further. These are all alcohols because they contain the functional group, and we've got to be careful here because I'm about to show you compounds that contain an alcohol but aren't alcohols. What? Because we've got to make more complex functional groups by adding pieces together. This alcohol does not contain anything else. No carbonyls right there, no double bonds right there, that's just an alcohol. Where do they show up? Simple example from the lab, cyclopentanol, and obviously a more complex example from nature, cholesterol. Okay? We haven't talked about the names yet, but the ol at the end of the cholesterol tells you it's an alcohol. It's kind of how the names come about. So alcohols must have an OH group. Move further, ethers. Ethers are confusing. People get ethers mixed up with esters. They sound the same, but they're quite different. An ether is an organic molecule which has carbon bonded through oxygen to another carbon. This is dry, this is mundane, but it's essential. Flashcards, whatever you need to do to get this worked out, so that whenever I say the words, you know what it is in your head. These are ethers. We have Batman ether right here, which is kind of fun. We'll talk about that a little bit later. 2 lone pairs, we've got carbon sticking off of them. We'll find that useful in the lab. Mr. Benedetto. Carbon, oxygen, carbon. Carbon, oxygen, carbon. I can say it in English for you. How's that? Right. Your job is to recognize the pattern. These are all patterns. So you go to brevetoxin B, this outrageously complex natural product. It's all ether chemistry. Over here, this is an ether. Carbon, oxygen, carbon. That's an ether. Carbon, oxygen, carbon. That's an ether. Not too tricky on its own when it's broken down into its basic components, but you start to put this into a complex molecule, you've got to be on your toes. These are straightforward points on exams that you need to get to build that grade. More complex. Not so useful to us as chemists, more biological. If you take biochemistry, you'll certainly see a lot of these things. Thiols. They are the sulfur equivalent of the alcohol. You've replaced OH with SH, and we'll call it a thiol. Thi being a precursor part for sulfur, and ol being similar like the alcohol functional group, thiol. Very simple ones you'll see in biochemistry. You always know when people are working with these things because they stink. They are nasty. They're probably the one you've dealt with before in freshman chem is this stuff. Okay, butane thiol. If you use a Bunsen burner in the lab and you turn it off or you forget to light it and you start to smell something, you smell gas. You're not smelling gas, you're smelling this. So natural gas has no odor. But of course, in an environment like a laboratory, you need to know if there's a gas leak. So they put a little bit of this stuff in there, butane thiol. You can definitely smell that from a distance, right, at very low concentrations. So this is a thiol that's put in there to make things safe. We'll talk about their chemistry a bit later on, and we'll talk about their acidity coming up in chapter 3. In biology, you'll use these things in different experiments in biochemistry. And if you take, for example, Dr. Sturman for biochemistry later on, she's an expert on glutathione, so you'll probably learn something about that in terms of its uses, for example, as a free radical scavenger. So this molecule, a lot going on. There's the thiol. We haven't talked about these yet, we will in a minute, but the one you're looking at right now is the thiol. SH thiol. Second type of sulfur compound that you have to worry about is the ether equivalent from sulfur. Why do I say equivalent? Well, look at the periodic table. Sulfur is below oxygen. They're closely related. So you'd expect sulfur to do similar things to oxygen, and it does. And this is very useful because sulfur can do things oxygen can't. Sulfur can have 6 bonds, you know that. It can expand its octet. So sulfur will become very useful as sort of a malleable material that can be used to expand things and make different structures that oxygen cannot. Idea again, you watching Mr. Benedetto? Carbon, sulfur, carbon. That's a sulfide. We also call it a thioether. There's a bunch of stuff coming up about those later. But recognize it and be happy with it. Michaela? Yeah, go on. They are sulfur with 2 carbons attached. Because if you think about what a thiol was, it was sulfur with a carbon on one side and an H on the other side. That makes it a different functional group, and it makes it chemically quite different. Mr. Drysdale, are you happy? Good man. So now, second semester, a huge amount of benzene chemistry because it's very important. This idea now of looking at these cycles, that's benzene itself. This is naphthalene. You've probably dealt with that as mothballs. You can smell this stuff. It smells quite nice. They show up all over the place. This is a benzene ring. We might call it something a little bit different later, a phenyl group. But we'll call them aromatic, which is another nonsensical thing. I'll explain that next semester. But these are called arenes or aromatic. Okay? Arene is sort of a bigger group of molecules that can contain nitrogens or sulfur or whatever else. They all have this 6-membered ring type system so far, in which you have this 3 double bonds. So they are identified as arenes. I'm not going to finish all this today, but that's fine. You've got time to do some of this stuff now. Doesn't mean I'm done. I'm going to talk about ketones very quickly. A ketone is a carbonyl. It has C double bond O in the system. And that C double bond O will be a large part of the second term, deciding what they do. Very, very important compounds in things like fission processes and things like making fatty acids when we have to couple things together later on. So be comfortable with these things. We have a carbon, which is not shown because we stripped it out, next to an oxygen. What's the delta plus on here? Delta plus, delta minus, what is it? Delta plus. What's missing from my O that I really should have there? Lone pairs, and it's delta minus also. Acetone we already talked about from the lab, and then things like progesterone, when we talk about hormones. There's a ketone right there. It's buried inside that molecule, and the definition is a carbon with a carbonyl with a carbon. Not a carbon-oxygen carbon, but a carbon with a carbonyl with a carbon. Starting to get confusing, starting to get very similar. But that's what this class is all about. It's the margins. It's making sure you understand the detail and the minutiae so that we can go forward. So last thing to finish off, and then we'll come back on Friday. They're cousins, the aldehydes. And aldehydes are different. They are chemically quite different. They contain a carbonyl. They contain C double bond O. They have the same polarity here and here, but they do quite different chemistry to ketones. In this case now we have carbon bonded to a carbonyl, bonded to a hydrogen. Very subtle difference will make all the difference next term. Examples of this, benzaldehyde. Okay, smells like almonds. You've got a hydrogen there, you've got a carbon there, that's an aldehyde. Cinnamaldehyde, smells like cinnamon. Carbon here, hydrogen there, they're aldehydes. By Friday, I want you to know those. And then we'll do the rest and we'll finish up chapter 2 probably on Friday. Okay, get some work done.